All right, we're going to go to section 7.4, Rules of Replacement 2. So there's 5 more rules of replacement. I'll quickly go over them, and then this video will mostly be 5 examples, okay? So the next, let's go to 14 here, transposition. All this is if you have a conditional, you can you can swap the antecedent and the consequent and just negate them, okay? So if you have if P or Q, and you may find sometimes it's going to be helpful to switch this conditional, okay, and put tildes in front of the variables. And one of the examples, I believe, I'll show you where this can come in handy. Then you have material implication, and this is very helpful. It will turn a horseshoe into a wedge, a disjunction. So a conditional can go to a disjunction or vice versa, and that's going to actually come in handy, okay? Here, let me make that a little better there. So keeping track of these operators really helps. So you can go back and forth between a disjunction and a conditional. Okay, that's material implication. Material equivalence, you know, here's your biconditional here. Okay, just so you know what the equal sign means again. On the keyboard, I use that to represent the triple bar. If you have a biconditional P if and only if Q, that can be replaced with if P then Q, not if, I'm sorry, both if P then Q and if Q then P, or this is another way to express it. It can be a disjunction. So a biconditional can be re-expressed into a dot operator, a conjunction, or a disjunction of 2 conjunctions, okay? Then you have exportation. And if you have an antecedent of a conditional as a conjunction, you can replace that with, you know, if you have if both P and Q then R, you can replace that with if P then if Q then R. And so we'll use these, and you'll just, you know, see some examples of how this works. And then tautology, P can be replaced because it's equivalent with either P or P, or it can be replaced because it is equivalent with both P and P. And the reasoning behind this is, remember, a disjunction is true. One of the ways it's true is if both of the disjuncts is true. So this is true and that's true. So if you have P and it's true, it's the same as if you're just affirming, you know, you're either saying either this P, which is true, or that P. So if you got to pick one or the other, it's just isolating out the one. And remember, for a conjunction to be true, both P and P, both P's have to be true. So if you know both P's are true in a conjunction, then if you have one of the P's over there, well, it's also true. Okay, don't worry too much about some of the theory. Sometimes I like to bring in the theory just to kind of show you what's going on. But you want to pay attention to how you use these in natural deduction. So let's quickly just go to examples here. To the examples, there's 5. All right, let's do this first one up here. Not A, and we're trying to derive. If not A, then B. Now remember, we have a conditional here. Now we know we can add something on to A, and every time you use addition, right, you're going to turn the proposition into a wedge, a disjunction. So it doesn't take us hard to see, you know what, if I have a disjunction, I know through implication, and over here we're doing scratch work, implication can turn a wedge, you know, you can turn it into a horseshoe, right? So that's what I'm thinking. You know, those are the breadcrumbs. If I have to end up with a horseshoe and I start with this, well, I'll just add B. So that would be one addition, right? And then, because I've thought ahead here and I'm working backwards, you work backwards in your mind and then you proceed forward. So that's really what it did. I worked backwards. And I know if I add a B, I have a disjunction. And once you have a disjunction, you can use implication. And actually, you'd be going this direction on the little flap in the back of the book, right? Because the wedge is over here. And you can go that way to get the horseshoe, right? Okay, so if we have A or B, we can go this way. If we go back to right here. See, here's implication. The disjunctions on this side, we're going that way. Because remember, with rules of replacement, you need to get familiar going in both directions. So we're going back that way. And if I have a disjunction going back that way, I can use implication. I'm going to have if A, then B, right? And that would be 2 implication, because when you go this way, this left disjunct, you remove the tilde and you change the operator, and that's exactly what we did, okay? If not A or B is the second premise. And because we have a disjunction, we can go this direction and get the conditional. So remember, with all these, you're working backwards to realize what steps do you need to go forward. So you work backwards, you imagine it, you work on your strategy over here with scratch work. I do a lot of scratch work, everybody. Sometimes I look at a problem, I'm not sure how it works, because my brain isn't that good sometimes. And so I'll do scratch work. So you work scratch work to see if going backwards you have a plan that you can just write out forwards. Okay, so that's how we do example number 1. Now number 2, this is very interesting here. How do we get a G when we don't, we see 2 G's and we can't figure out a way to isolate them? Well, if we're working backwards, my breadcrumbs are telling me that, you remember that rule of inference called tautology? If you have either G, or G and G, well, these are both equivalent to G and G, right? If G is our P. So if I'm going to have to conclude with a G, and there's no way to really isolate them by themselves with what we're given, I know if we can get 2 G's together, then there is a way to get it down to a G. You can start with 2 G's and go down to the 1 G. That's what tautology is, right? And since they go both directions, if I can get 2 G's together by either a disjunction or a dot, then I can go in this direction, okay? So when I'm looking at this, I'm seeing some breadcrumbs. I see a conditional, and I know through implication I can turn this into a conditional. And if we have 2 conditionals, we can use HS and get the 2 G's together. And if I can get the 2 G's together into a horseshoe, then I know with implication I can turn a conditional into a wedge. And maybe I'll end up with something like this. So I'm thinking, let's get this into a conditional. Okay, if we use implication, that would be not F, then G. That would be 2 implication, right? And then I'm looking at everything here, so we're not working with that. I got this into a conditional, and I'm hoping 3 I can work with 1. So if I was going to bring those over, because I want to get these 2 G's together. If F, then G, and right here I have not F, then G. So if you were fiddling around with this, you go, this is not going to work. And the G is in the wrong place, but I'm noticing if I transpose this, if I go if not G, then F, right? If I just switch these and negate them, right? do that. I'm thinking transposition. So if I use transposition right here, you see how it gives me a conditional because I've done this, everybody. I've switched this line 3. If I switch it, my mind is thinking, now I have an F, and I have an F up here. This is going to work. Okay? So I would have this. I've switched this, so we'll kind of get rid of that. And if I bring this down so you can see this, if F then G, we can get if not G then G. And see, I've gotten the two G's together, and I know I can turn this into a wedge. So let's do this. I think we're on the right track here. So we're going to transpose, and oh, that's supposed to be a 4, isn't it? Okay. So I'm going to transpose line 3, and that will give me if not G then F, and that'll be 3 transposition, and then I can see that I can use that with 1, and 1 and 4 is going to give me if not G then G, and that would be 1, 4, HS. Okay? So I use line 1 with line 4, and I can get if not G then G. Okay? Then I've got the two G's together, so this is looking better. Everybody see that? And look, I can just use implication, because when I was thinking backwards, I can turn a horseshoe into a conditional, and this gives me either G or G, and that's 5 implication, and then from there 7, that is equal to G, and I would say 6 tautology. Okay, and there we go. That's how we derive that. All right, let's go to the next example, third one. All right, so we have one premise here. All right, now this is interesting. I see J, K, L, and we're supposed to derive if K, then J, L. So this is, if we were going to look at the order is K, J, L, right? And this is J, K, L. So we can see we need to get a K and a J, and we have a J and a K. And if we could get J and K switched, so it is KJL, looks like we're close, and there is something that can help us do this. You remember exportation. If we go this direction with exportation from your first page of the handout, the antecedent is a conjunction, and remember, a conjunction with commutativity, we can switch it. So why don't we do that? Because then if we switch it, I think we're at least getting the order, okay? So if we used exportation on this and went this direction, we would get if both J and K, then L, right? That would be 1 exportation. And then 3, let's just switch this, then we get our KJ, right? So we'll switch if both K and J, then L. That would be 2 commutativity. And this is easy. Let's just use exportation back the other way. And that would be if K, then J, then L. And that would be 3 exportation. Okay, so there's an example there. Let's go to the next page. You've got a couple more here. Oh, hey, all right, right here. if two premises, if m then n and if m then o, and we're trying to get if m then both n and o. So I'm seeing here three variables, m, n, o, and this is often what you see in distribution, okay? So here we have three terms. We see the n and the o are there. How are we going to get these two together? And then we have this m off to the side. Well, this smells a little bit like distribution. If you use distribution, usually, I mean always, it's with a wedge and a dot. But if you have distribution going a certain direction, you can isolate that term that appears in both expressions that are conjoined or they're a disjunction, right? If you have four terms but there are three distinct ones, distribution enables you to pull out the one that appears twice. Let me look at my handout here. Distribution, if you're starting from the right, with distribution you're starting from the right, you can pull out that third term. So this will make sense. So let's try distribution. First I'm going to conjoin these two, okay? Let's go if m then n, and if m then o, I would say 1, 2 conjunction, lines 1 and 2 conjunction. Now, some of you may be going, well, Dave, why are you using distribution? These are horseshoes, and we need these to be wedges. Well, we know through implication you can turn a conditional, horseshoes, to little v's or wedges or disjunctions. And I'm liking how this is looking, because with distribution, if we go this direction, right? If we go that direction with distribution, we'd pull that m out. So I like where the breadcrumbs are going here. So let's just do implication on these. It would be not m, then n. So this is the axiom of replacement. We can replace this with this. So if either not m or n, no, both, if not m or n, and actually, let me say that again. Both not m or n and not m or o. Okay, so that would be 3 implication, right? And you see what happens when you have this rule called implication. I know I can conjoin these, even though it's horseshoes. I'll convert them to disjunctions. And then I have a dot and a wedge together, and I know with distribution I could go the other direction. So there's implication. Let's pull out this m, okay? So if we were using distribution going this direction, right, and that is rule of replacement number 12, you go pull that out, the flap in the back of your book, we would pull not m out, and since this is a dot up here, distribution will change it to a wedge, and that means in the parentheses we have n and o. So this is 4 distribution, okay, and then 6, we'll just use implication on this. If m, then n dot o, and that would be 5 implication. Okay, so you look for breadcrumbs, you figure it out backwards, and when you do the proof, you proceed forward. So really what I did is this m being isolated and the n and o, and I saw the 3 there, you're already kind of smelling distribution. You conjoin them, and you know horseshoes can go to wedges, and once you have the wedges, we're all set up for distribution. It pulls that m out because the m is by itself. It keeps n and o together, and we're home free. Okay? So that's how we worked on that 3 implication. I'm just making sure everything's accurate up here. Okay, and let's go to the last example that I'll do for you, the fifth one here. All right, here is where we would like to deconstruct. Remember, if you get a biconditional or something, let's replace this with if P, then R, and if R, then P. Okay, and then what this boils down to is we have two conditionals that are conjoined, and this makes it simpler. Let's just see if we can get each of these conditionals by themselves, right? And then we can just conjoin them, and after we do that, we would go backwards and replace it with the biconditional. And so we're going to be using equivalence, right? Okay, well, let's see if we can get the if P then R. I see if P then Q, and I see the Q and R, and I know if I transpose 3, which would be if Q then R, it's because I just switched this, right? So 3 transposition, and the Q then R, can't you see if we had if P then Q, if Q then R, through hypothetical syllogism, that gives us if P then R. So we already have one of these. So let's put that down. If P then R, and we used 1, 5, HS, right? So we're done with that one. Now this really becomes reduced to how can we get if R then P? Well, I see a conditional with R in the right place. But right here, the variable that's going to snake around in hypothetical syllogism, right? Snaking around is this. These two have to be the same, equal to each other, right? Well, if R then both S and T, I don't see that here. I see the P in the right place, but I know with exportation it's going to give us what we want. So let's do exportation on line 4, and we will get if S then T, then P, right? If you go, that direction with exportation. So we're going to go for exportation, and then now we have everything we need. If R, then both S and T, it snakes around, right? If both S and T, then P. So we're going to get if R, then P. And let me just highlight this again. Here's the P. This whole thing is the Q. Through exportation, we've gotten the Q. This is the R. And therefore, we have if P, then R. And if you wrote that out, that's hypothetical syllogism, right? Q, then R. If P, then R. So that's all we did there. Okay? And let's get rid of those. Okay. Now let's conjoin those two. Oops. Let's get that black. Okay. So let's conjoin our two conditionals. If P, then R from line 6, and if R, then P, that would be line 6 and line 8. That would be conjunction. And we forgot to, let's draw this in here, 2 and 7. 2, 7, HS for that one, right? Okay, and then let's just replace that with P if and only if R. Okay, and that would be 9 equivalents. Okay, and there's 5 examples of using the next 5 rules of replacement. We call them rules of replacement 2, and that ends all 18. So hopefully this has been enough examples and explanation to help you get going on this.